So if we're going over, oh yeah, I can't do that. Exploring reciprocals of trig functions, okay? So we've used the chart to essentially fill out our cosecant x. And we have our degrees and our radians here, okay? Now the one we do technically know very well is our sine x, right? So when x is 0, sine x is what?
0.
Yeah. What about when it's 30? What does it give us?
Half.
A half. When we're at pi over 4 or 45 degrees?
1 over root 2.
1 over root 2. When we're at pi over 3?
Root 3 over 2.
Okay, root 3 over 2. Yeah?
1.
1, good.
Root 3 over 2.
Yeah, it's following a pattern
1
again.
over root 2.
Yeah.
And half.
And then
0.
0 again. Okay, good. So the reason we've put those in is so we can get an idea of what we're drawing here. Now, in this graph on this page, we really only, it hasn't been condensed nearly as much, okay? But we're going to notice a pattern here. We know that in between, so at root 4 or 45, we're actually at 1 over root 2. What is that approximately? Because we don't have our y values in terms of roots. What's 1 over root 2 approximately?
0.70.
0.7, okay. So they're saying that it's roughly here, okay? Then again, that means this is roughly there. So when we follow this pattern here for our sine wave, we know we're coming up and down. And then the same negative pattern continues after 180 degrees, correct? We go down to -1. This one would be at -0.7, -0.7, and 2 pi brings us back around. That's how long the period of this function is. Okay? What we discovered with our cosecant is that we have asymptotes, so we're undefined at the points where we'd be 0 on sine. So in other words, we're taking, and we'll do it in a different color, we're taking our 0 values and drawing lines through them. At those points, our cosecant doesn't exist. Okay? And what we've also done is we've gone exploring with cosecant to figure out what actual values we have. So at 30, which 30 degrees is pi over 6, would be somewhere over here. We're looking at maybe 2, okay, as our y value. That's what we're talking about. 30 degrees, pi over 6, we're looking at 2. So we kind of estimated where that was on the graph. Next one was 45, so that's right in the middle. And that's where on sine it was 0.7. We have 1.4. So we're probably about here-ish. Okay. And then at 60, gets a little closer. We're going to skip 60 and go straight to 90. 90 is at 1. So that same peak, or that max point, becomes the minimum point of our reciprocal. Okay. Then again, because it's symmetrical, it comes up, and then about here. So what we're looking at is, because these are asymptotes here, they're going to continuously get closer and closer. Oh, that didn't quite do it, but get closer and closer and take off towards this way. They'll never touch those lines. They almost look like quadratics, except that there's asymptotes beside them, right? So that same idea happens, and now we're going to zoom in on the other page. So we've already written the actual values here. We'll zoom in on this page so that we can kind of try to continue this pattern. Okay, so if you know our sine functions like that, that means this minimum is probably going to be a maximum of a cosecant function, right? We know we're going to have a value of about 1.4 halfway below it, so negative 1.4 or something like this. And then at 30 we'll be at 2, so we're getting that U shape, okay? But this one's just going down instead. And then it's going to get very close but never touch that asymptote. So essentially what we do is we can use, and we'll zoom out a little more, we can use our sine wave, because we know it's going to come back up like this. And we can continue it this way also. We know that this sine wave will continue this pattern. And with that, we can easily draw our cosecant. We specifically explored them to make sure we were getting the right idea. But now we know we have the right idea. We can kind of estimate what our graphs are going to look like from there. So let's we'll draw our other asymptotes, okay? We have 2 other asymptotes here. And instead of actually picking out the points, we know that, well, this is going to be a minimum. We're going to be about here and here, and then maybe here and here. We draw maybe 2 other points each way, but essentially this is the general idea if we're doing rough sketches of it, okay? And with that being said, here's our general idea, right? Now we're getting the hang of it. We know what this function is probably going to look like. From here, we can start to do transformations of the function, okay? So we've explored what it looks like. Okay, now what we're going to talk about is our transformations of cosecant. So we'll jump onto a new page here. Okay, so if you remember, we talk about f at x when it's equal to a, whatever the function is, k, yeah.
X minus D or plus D.
Yep.
And plus D.
Plus c, good. Well, in this case, the function is what?
Sine and cosecant.
Cosecant, right? We've done sine before. We know how to transfer that up and around. Now we have the a value on the outside of it, so our f at x is equal to the a value of cosecant. We have our k, x, we'll say minus d, and then plus c on the outside. We know a and c deal with either vertical vertical compressions or shifts, right? C is doing the shifts, A is doing the stretches, and we know our k's deal with horizontal movements or shifts. Okay, so for instance, let's just say we'll make a question up here. Do they have one? They do have one. Great. We'll take it. They've written it as y, which is fine. Y cosecant
Bracket x plus pi over 2.
X plus pi over 2. Okay. So what values do we look like we have here?
K.
Okay.
D.
Which is our k?
2.
2. Okay, we have k is 2, and our d is what?
90.
That's right, 90 or pi over 2. So in other words, this is going to be a shift of which direction?
To the left.
To the left, right? Because we know positive actually goes in a negative direction. To the left of pi over 2, which is also known as 90 degrees. Okay, so in other words, this entire thing is going to shift 90 degrees. And then what's going to happen is it's going to become what?
Half. Like you multiply all x's.
So the period is going to be happening twice as fast, right? We know our old period was pi over 2. It was the same as our sine function, right? So our new period is actually going to happen every pi when we go to plug that in. So what we can do is actually play with these values to explore them also. So we'll go to our chart again, and we're going to plug values in for this to actually figure them out. Okay, so let's pause this. We can make a chart. Okay, so what we've got now, single page. Okay. We've got this information. The best way to really get an idea of how to graph this is to apply the same movements to a normal sine function. Okay, so let's take those exact same movements, and we would say sine, our k value still being 2, x plus pi over 2, or 90, you could say. Okay, and we know that's going to be our k. It's going to increase the period's going to occur much more faster. Like we said before, a normal period in the inverse is 2 pi. A normal period with sine is 2 pi, but because our k value is 2, we divide it by 2. Our new period is going to be pi. Along with that, I did pi over 9. It should say pi over 2. I was thinking of 90 degrees. Pi over 2 is also shifted of 90 degrees to the left, right? So let's actually go about graphing that from the original. We'll get a new page up, and we'll take degrees. No, we'll go in radians because we do know our stuff with radians. Okay, so our normal sine function occurred like this, if we recall. Okay, and we know it continues the other way also. Okay, but what we said was because of our movements, we have y is equal to sine 2 x plus pi over 2, right? First of all, we knew that what's going to happen is our period's going to happen twice as fast, correct? So what that means is our peak is going to be at 45 degrees. We're going to come down. This will be our new 0. We come down here, come back up here, okay? So that's one shift of the sine function. Does this make sense to you?
Yeah.
Yeah. So that's the first shift. That's just for the k, okay? We actually haven't, sorry, that's the compression. We actually haven't shifted anything, okay? So that's just a compression. In other words, that would be sine 2x, okay? And now we're going to add the pi over 2. Well, the pi over 2 is going to shift everything 90 degrees. So this 0 now occurs over here. This upper point occurs here. And this other 0 occurs down here. So we'll do it in a different color, obviously, so that we can tell the difference. But our new function is going to look like this. It'll be the red one, which will be hard to see, but we'll redraw it on its own. Okay, so our new function is the red guy, and he has been shifted 90 degrees. Okay, so that would be of a sine. Y is equal to sine 2 x plus pi over 2. Okay, so we got that information. We're going to jump to a new graph with just that one, and then we're going to draw the reciprocal of it. So let's get our reciprocal of this, of our radians. If you recall, it was happening, I think, like this. Does that seem right to you?
Yeah.
Okay. So we're going down like this and up. We'll just quickly put all of our points in. So this was our function, with our sine function with the compression of 2 on our k and our shift of 90 degrees to the left. So here's our new sine function. The reason the new sine function helps us out is because it gives us what our new zeros are going to be on x. Okay, so that was of y equals sine 2x plus pi over 2, right? Let's get a new one. So now since we actually have zeros, we'll do them in red. We have new sets of zeros essentially occurring twice as often. We have twice as many asymptotes going through this for our reciprocal of the function. Okay, and we'll talk about that again. We still have one still on the y-axis. Okay. So here are all of our asymptotes, and this is for the function, this is what we're really trying to graph. Y is equal to cosecant 2x plus pi over 2. So we just applied those to our sine waves. And then from there we take the exact same mentality we had before. Our maximums and our minimums are actually going to be the reverse, the minimums and maximums of our cosecant. And the asymptotes we're going to get very close to but not actually graph. Okay.
So I have to draw the sine and then...
It will be very helpful to draw the sine one first just because it's one we're a lot more familiar with. Yeah. Now, technically, you may be able to just look at an original cosecant one if you're very confident with drawing it. But if you're normally drawing the cosecant from a sine wave, it's probably just as apply the transformations to a new sine wave and then draw the cosecant from there. And again, this pattern is just going to continue, so I'm going to get a little sloppier as I go through it, okay? Yeah. But that's the idea. So if you notice, and we'll count the period out, the periods of these functions are happening twice as fast because of our k movement, okay? So if you take a look, let's say we're at R0, okay? We know that this is 1 point. Well, one of the periods occurs all the way back here. That's when we start over again. So we've gone down and up, if you've noticed. You notice that we had one that goes down, one that goes up, and then the one that goes down again starts at the pi, right? And we went from 0 to pi, where normally that would take all the way here. So in other words, normally our cosecant function actually looks like this. And then our other one, I'm going to try to eyeball this as best as I can, would look like this. Okay, those blue ones there. And then if you notice, where we normally had 2, we now have 4. Okay? And everything has been shifted 2 to the left. That's also a little bit of a difference compared to what we had before. Because normally also, because everything's been shifted to the left, usually from 0, our cosecant, the first one is going up, if you recall, right? Well, if this guy had been shifted to the left, let's say 180 degrees, because there's also compression involved in there, he would be all the way over here. Does this idea make sense to you?
Yeah.
Yeah. So he would have shifted all the way over here, and which now means the first one after 0 would have actually been facing downwards. Hence why this cosecant is facing downwards. It's a shift of 90 degrees to the left. So that k really plays with our d value, our shift in the function, okay? So let's see if we have a dual page. Yeah, so that's how we got our sine wave transferred, and then we put our cosecant from there. And that was our original one, okay? So maybe even, let's see if we can't, nope, that's not the one I wanted.
And like, I have a question, Kate. I know how to draw the dot because it's just the opposite, but then the actual branches, can I just draw them in?
Yeah, you can just draw them in, because remember when we did this here, those points, we estimate them, we have a good idea of where they're going to be. If you want to memorize a couple of the other points, like the one that's at 1.4 or at 2, which is at like 30 and 60 degrees, I think it is, something like that, then you can. But Otherwise, you can kind
You
of
can just
just
draw it?
eyeball it. Yeah,
Alright.
that's what we're going for.